back to your Dynamics of Rigid Bodies. Okay, we will now proceed with your Module 3. It is the Kinetics of Particles. So, under this, we will be discussing the first unit, which is the Newton's second law. Okay, so again, if you will try to recall your physics, you discussed the three laws of Newton, isn't it? So, we will try to recall this, but for this topic, we will focus on the application of Newton's second law to our dynamics of rigid bodies. Okay, so in this unit, you will be expected to have these learning outcomes. First is to state what is Newton's second law of motion, and of course, we will try to understand this one. And then, of course, we will try to apply this Newton's second law on problems involving this one, okay, this topic. So we have here your first law of Newton. Okay, it says there that in the absence of external forces, an object at rest remains at rest, and an object in motion continues in motion with a constant velocity. So, okay, so that is your first law of Newton. It says there that if you have a body which is at rest, that will remain at rest unless you will be applying an external force. Okay, so that the state of that object will change. Or let's say you have there a moving object at a certain speed, and that will still that will move continuously. It will not stop. It will not be changed. The motion will not be changed unless there will be an external force that will be applied on this motion. But if you will try to observe this one on actual life situation, there is no such as this continuous motion, because there will always be this what we call as the friction. Okay. So, for example, let's say you are going to roll a ball on a ground. That will not continuously moving, because, of course, of the motion between the ball and the ground. So, at a certain time, that will be expected to stop. Because again, what happened there is we have this friction, which is actually an external force. If we say external, it is not produced by the ball itself. Okay. It is interference with the motion. So that causes the change in velocity up to the time it will stop. But eventually, if there is no, let's say we will consider here an equilibrium, or let's say we will be considering an environment which is a vacuum environment, so there is no external forces, then if that is in motion, then that will remain in motion. And if that is at rest, then that will remain at rest. Okay, that is the first law of Newton. Again, as I've said before, we will focus in your second law. So first, we will try to recall what is the third law. Okay, so later on, we will go to the second law. So in the third law of Newton, it says there that if two objects interact, the force F sub 1, 2 exerted by the object 1 and on object 2 is equal in magnitude 2 and opposite in direction to the force F sub 2, 1 exerted by object 2 and object 1. Okay, so that is, it seems like complicated, but let's say you are just considering here two objects. Let's say this is object 1, that is object 2. Okay, if they will interact, if we say, let's say they will bump together with each other, the force that is acted by this object 1 on object 2, so that is what we say there on your presentation as the F sub 1, 2. It means the applied force by the object 1 to your object 2 is equal to the magnitude but opposite in direction by the force applied by 2 in your object 1. So again, that is just actually what we call as the reaction, and you had that one in your physics, isn't it? Reaction. And so with your rigid bodies, your statics, you discuss what is reaction. If you're going to apply a certain force on something, you will expect a reaction that will be going back to you. Okay, so that is an opposite direction, but always summation of, for us to have to satisfy the equilibrium equation, what you apply, that should be the same on what will be applied back to you. Okay, so that is your third law of motion about reactions. Now let's proceed with your second law of Newton. Okay, so this is what we will be focusing in this topic, the second law of Newton. So it says there that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Okay, so what does that mean? Actually, this is this first equation here. A is equal to F over m. Okay, so that is your second law of Newton. Acceleration is equivalent to the force over mass. So it says there that your acceleration is directly proportional. So what does that mean? If we will try to increase the force applied on an object, then the acceleration of that will increase also. That is the meaning of your proportionality. By the way, we have here an example. You can read that one. Okay, an example here below. But okay, I will just explain it briefly so that our video will not be that long. Okay, so again, your acceleration is proportional to force. So let's consider here an object. If you are going to, let's say, exert more effort on an object to start an object, of course, the bigger the acceleration will be. Okay, the bigger force you will apply on an object, the bigger the acceleration, the resulting acceleration on that object for that to move. Okay, if that will now move. And of course, that acceleration is, however, inversely proportional to its mass. So what does that mean? Again, if you try to analyze the same object, let's say you applied a certain force. Let's say you will apply a 10 kilonewton on an object, on a certain object. You will be having an acceleration. But what if that object will change? Let's say that object will now become bigger, or let's say, since we are talking about mass, that will now be become heavier. You will apply the same 10 kilonewton force, you will expect a slower movement because that increases the amount of that, or the weight of that increases. Isn't it? You can observe that one on actual life situation. Or if you are going to push a smaller object, of course that will move faster compared to pushing a big object. Okay? So again, acceleration is proportional to force applied, but inversely proportional to its mass. So if you will try to rearrange this equation, cross multiply m into your a, you will have the force is equal to the mass times acceleration. Okay, so that is how we will rewrite your Newton's second law. But this is the original. A is equal to F over m. Okay, so again, you can read this one, and that is another example for that. So before we will go to the problem solving dealing with second law of motion, Newton's second law of motion. Okay, let's try to discuss what are these. Okay, first is what is free body diagram. Okay, you had this one in your physics, and you had this one also in your statics of rigid bodies. Okay, so okay, you can read again our definition here. This is your module, so there are a lot of definition and explanation in words, but actually I can just show you an example, explain it by oral, so that we will not be reading this one again. So it's up to you to read this description. Okay, so free body diagram. Okay, if you say free body diagram, that will be a figure representing the system that we are trying to analyze. So isn't it, in solving reactions, in your, what we call this one, statics of rigid bodies, you need to draw the figure itself. Okay, especially if your system is a little bit complicated, wherein you are going to analyze this one part by part. What you're going to do is focus on this part, solve whatever that you need to solve, and then proceed to another part of the system, and so on and so forth. So free body diagram is very, very important, wherein this will now expose every element in the system. For example, here in this figure here, you are going to push a book downwards. Let's say that is on top of a table, and you're going to push that one downward. So what are since we are referring here to forces, isn't it? What are the forces that is present in this system? Okay, or in this situation? Of course, the first there, the main force there in our system or in this situation is that the weight of the book itself. That is a force, isn't it? Weight is considered as a force. So that is, of course, the main force here, wherein that is actually weight is a product of the mass, isn't it? If you will go back again, their force is equal to mass times acceleration. But since weight is the force that we are trying to consider, then weight is equal to the mass of the object times the acceleration, wherein if we say weight, that is due to gravitational force, the gravity itself. So therefore, your acceleration will just be the gravitational acceleration. So if you are referring to a weight, that is the mass of the object times the gravity. Okay, you discussed that one in physics. Again, that is the difference of what is weight and what is mass. So you need to differentiate this one. Please do not confuse yourself with weight and mass. Mass is as in, that is a scalar. That's a scalar quantity, but weight is a vector. Wherein vector, it means that is directed always downwards. Okay, so again, the weight is affected by gravitational force. So that's why they are saying that weight is different on different locations. So let's say your weight here on Earth is different from your weight if you will, let's say you will go on the moon, because of course the gravitational force of the moon is different from the gravitational force of the Earth. Okay, so again, that's it. The first force that we will be considering on an object is its weight. Okay, its self-weight. So that is the mass, its mass times the gravitational force. And then of course, since if you did not push that one, that is the only force on the system, only its weight. However, you applied an external force there, wherein you applied pushing down that book on the table. So isn't it, going back to your third law of motion, if you apply the force on something, you will expect a reaction, which is opposite direction but the same magnitude. So that there is a reaction. Let's try to put that as N, or that is the normal force. We call that one the normal force. If you say normal, that is perpendicular to the action of the, perpendicular to the surface. So let's say that surface is horizontal, your normal force is perpendicular, so that means that is vertical. But if that is inclined, let's say the surface where the object is located is inclined, then that normal force is inclined also. That will always be 90 degrees with the surface. Okay, so again, that is your free body diagram. Draw the system and then try to indicate all the forces that is available. Okay, so that will help us again. By the way, because we cannot and we do not have right away your equations in your problem, so you need to create your own equation and then solve for what is being asked. So again, you will always start with a figure. Creating a figure, that is where you will be basing the equation that you will be creating. So that is the free body diagram. And of course, since we are talking here of movement in free body diagram, just like in our kinematics, isn't it? If there is a motion, there will always be a direction. So let's say you have here a complicated system and you do not know which direction the movement will flow. All you need to do is assume a direction. Okay, DOM, that is your direction of motion. We had that one in your kinematics, isn't it? So always assume a direction of motion, where in the direction of motion, every parameter going to that direction is positive, and a negative direction to that DOM will always be negative. Okay, and let's say you will end up with an answer which is negative. That only means one thing, that your actual scenario will be the opposite direction. Okay, so that is your free body diagram. You need to have also your direction of motion. Okay, so next is important for us to know friction again, but this is discussed in your physics, but let's try to recall. Okay, you can read again this one, but okay, let's say I will focus here on the figure. Let's say you have here a box, okay, and of course in this system you need to draw again the forces available, and actually first and foremost is your weight, the weight of the object itself. So if there is a weight that is directed downwards, there will always be a reaction. There will always be a reaction which is opposite. So that is your normal force. That is the reaction of your weight itself. And then, let's say you are going to apply here a horizontal force. That is your force F in our figure. You are going to push that one to the left. Then what happens? That will move to the left. But again, as we said on your friction, there will always be a resisting force. If you are going to push something that is on the ground, it depends on, of course, the roughness of the ground. So the force of the friction force depends on the roughness of the ground in the object that you are pushing. Let's say that is a box and you are pushing that one on, let's say, a rough surface. Then you will end up with a bigger resisting force. That if you say resisting force, that is the friction resistance. Okay, resistance for that movement to happen if you will apply a force horizontally for that to move. So you will always expect there a friction, unless again that the ground and the box is very, very slippery, wherein there is no roughness. So you will not expect there a resistance. But of course, if there is a roughness coefficient, actually that is defined by the roughness coefficient of the surface, there will always be a friction. Okay? So which is opposite direction to friction is always opposite direction to the movement. So if you are pushing that one to the right, the friction will be always against, so that will be to the left. But if you are pushing that one to the left, then the friction will be to the right. Or let's say you are doing it vertically, if you're pushing it upward, and that is on a surface, vertical surface, then you will expect a downward friction force or resistance force. Okay, so what else about friction? Okay, there are a lot of definitions written here or explanation, but of course here this is the important here. Okay, this paragraph. Friction force opposite. Okay, it is there. Friction force opposes. We have here the enclosed impending or actual. Okay, by the way, if we say friction, there are two types of friction. The first is the what they call this one, static friction, wherein let's say that is originally at rest, you are going to push that one, you are going to push that object, there will always be a resistance already, even if that is not yet moving, isn't it? You can actually try that one on actual. You will try to push something. If that is still at rest, you will feel a resistance. Okay, if that is what we call as the static friction. Okay, the resistance while it is at rest. So let's say you will start with a small force. You will apply a small force first, and that will still not move. So you will try to increase and increase your force applied up to the time that will now start moving. So once that is now moving, that the force, the friction that is applied or the resistance that you are feeling there is not already static, because if you say static, that is at rest. So again, then what is the resistance? If that is already moving, that is now what we call as the kinetic. So we put that one as the F sub S for the static, and then F sub K for the kinetic friction. Okay, so based on experiment, uh, always the what we call this one, the static friction is always bigger than the kinetic friction, and actually you can again observe that one on actual scenario, wherein if you will try to push something when that is still at rest, you will try to exert more effort. But if that will now start moving, you will now feel there that the resistance will now be smaller than or lower than the resistance while that is still at rest. Okay, you can actually do that one. So that's why, based on experiments, the static friction or the static resistance is always bigger than the kinetic, because once there is already a movement, there is what we call as the momentum. Okay, so the friction that you will that you are actually experiencing will now be lessened because of the movement. Okay, so there are two types, the impending and the actual frictional force, or that is the static and the kinetic. Okay, so here you have here the equations. So if you are solving the static force, that is just equal to this is mu, we call this one this is red mu. Okay, that is the coefficient of static friction. That is what I'm saying a while ago. If we say coefficient, that is the ratio of the force. That depends on the roughness. So the more or the rougher the surface is, the bigger this coefficient of static friction. And then of course the smoother the surface is, the lesser that static coefficient of friction. Okay, so that is just the multiplier. So how do we end up with the frictional force? That is actually a percentage of the normal force that is perpendicular on the surface. That is the use of your normal or your normal reaction, your force N, the reaction that is perpendicular to the surface. Okay, so let's say you will have there a normal force, your N is 10 kilonewtons. Then of course the percentage of the 10 kilonewton will be your friction. Again, as I've said a while ago, your resistance also depends on the mass of the object itself. The heavier the object is, it is harder for you to push compared to a lighter object, isn't it? So that is, the friction or the resistance is a percentage of the perpendicular force to the ground or to the surface. So again, as I've said again, that mu there is just the percentage. That is just a coefficient. So if you say coefficient, that is unitless. So if your normal force is in newtons or in kilonewtons or in pounds, you will expect that your frictional force is the same unit also. Since that coefficient is just a number. It is just a coefficient. It is just the what do you call it? It is just the percentage. Okay. And if you are, of course, solving here the kinetic friction, again, as I've said a while ago, the static friction is different from the kinetic, because the static friction is the resistance while that is still at rest, while you are trying to increase the force that you are applying. And then the kinetic force or the kinetic friction is now the resistance while the movement is happening. So as I've explained a while ago, kinetic is always less than the static, because you need to have this more power to start the movement than continuing that movement. Okay. So again, if you will try to solve the static friction force, you will use the coefficient static. But if you want the kinetic, then you will use the kinetic coefficient. But most of the time, if their difference are negligible, if the difference of the static and the kinetic coefficient are negligible, okay, you can now neglect the difference, then they will just be giving you a single value, or in that could be the static coefficient, or that could be also the kinetic coefficient, unless given that they are different. Okay, so these are the types of your friction: kinetic and static. So in general, your formula is just friction is equal to coefficient times the normal force. So if you need the static friction, then use the coefficient static. If you need the kinetic friction, then use the kinetic coefficient. As simple as that. So your general is just F is equal to mu times N. Or we are memorizing this one on board exam. Okay. For this to be embedded in our minds, friction is fun. Okay. If you will try to look at the formula, F is equal to UN. So you can just read actually that one as fun. So friction is fun. Okay, so that is friction. Okay, so this is also important points to remember if we are trying to solve problems regarding your second law of Newton's second law of motion. So first, okay, in all the problems on Newton's law of motion, proceed by drawing the free body diagram for each object in the system separately, and then solving for the unknowns. Okay, as I'm saying a while ago, if you have a complicated system, you will try to break this down into parts, okay, and then solve for whatever is being asked. And then again, this is important, consider the direction of motion as a positive direction. So if you do not know yet the actual direction, always assume. And then later on, you can check if your assumption is correct by looking at the signs of your answer. If that is negative, that means your assumption is just different, but the value is still the same. Okay? And then, of course, second is the mechanics. And this problem is to recognize the constraints that bind the different parts of the system, like the two objects have to move with the same acceleration and an object cannot lose contact with the surface. So this is actually an explanation on what will happen if the motion will go on. But actually that depends on the system. I will explain that one if we will go on the problems. But actually read this one, you can read this one and understand, but it is better if I will explain that one during the discussion on the problem itself. Okay, and then number 3, a string have some tension in all the points. Again, so this is applicable. I wrote this one only because most of the time the application of this on problems are sliding objects that is connected by strings. So okay, so it says there a string has some tension in it and in all points, each in infinitesimal part of the string has the same tension, trying to pull it apart on an opposite direction. So let's say, okay, for example, I will consider here two objects, and these two objects are connected by a string, so that the movement of the other object will be the same movement of the other object. So let's say we will connect these two objects by a string. So the movement there will affect the movement of the first will be the same with the second because of the string attached. So what do you expect? There will be a force that is exerted on that string. And of course, because that is moving away and this will be being dragged, you will expect that the force on that string is tension. If you say tension, that is being stretched, isn't it? You discuss what are the forces on your statics. You have compression and you have tension. So most of the time on strings, the purpose of the string is for tensions. Okay. And then, okay, for example, again, this is a system, isn't it? If you will consider the movement of these two objects because of the connection of a string, if you will try to analyze this one, cut this string, and then consider the free body diagram of the first object, and then go to the free body diagram of the second object. So what do you expect there? They will be separated. So if you will try to cut the string in between, you will expose there the force that is applied or that is being experienced by that string. So okay, I will explain that one further if we will go on the examples. And then of course, an important points to remember, the fourth is that weight is always mass times the gravitational acceleration. This is just a force, wherein a force is a product of the mass and the acceleration, but we are referring here to the force which is due to its mass, so that is the weight. Okay, so now let's try to have examples. So example number 1, a ball of mass 5 kilograms and a block of mass 12 kilograms are attached by a lightweight cord that passes over a frictionless pulley of negligible mass as shown in the figure. Okay, so you can see here in this figure, and then it says there that the block lies on a frictionless incline of angle 30 degrees. Find the magnitude of the acceleration of the two objects and the tension on the cord. Take J, or the gravity, to be 9.81 meter per second square. Because actually, if you will try to look at our units, even if that is not given, you will expect that that is the gravity that you will be using because we are on metric. Okay, so that is your gravity. So if you will try to look at the figure, we have here a ball which is 5 kilograms, and we have there a box which is, or a block which is 12 kilograms. So for example, okay, actually this is already the solution, but for example, in the first place, there is no direction of motion yet. You do not know what will happen here. Okay, so by the way, this 5 kilograms ball and that 12 kilograms block is connected by a string. So that means that if there is a movement in this 12 kilograms, then there will be a movement also on that 5 kilograms. Or that is vice versa. If there is a movement on this 5 kilograms, then there will be a movement on the 12 kilograms. That is the use of your string attached. So that is what I'm explaining a while ago. So this is your total system. But if we are going to analyze this one, since you cannot see their actually forces, we will try to expose that one by cutting your string. So we will focus on the free body diagram of your 5 kilograms and then go to the free body diagram of your 12 kilograms for us to again to expose the force that is experienced by the string, which is actually one of the unknown, that is the tension on the cord. Okay, you had that tension and compression forces on your statics of rigid bodies. It says there that also that that block is lying on a frictionless. Where's that? This one. The block lies on a frictionless incline, so there is no friction. There is no resistance being experienced by that 12 kilograms if that you will slide, because maybe that inclined surface is very, very smooth. So the friction or the resistance is negligible. So there is no problem about friction here since that is frictionless. Later on, we will have an example wherein we will encounter a friction due to roughness of a surface. Okay, so however, that is inclined at 30 degrees. The surface is inclined at 30 degrees. So again, let's say I did not yet put there the assumed direction of motion. So how do you know if these 5 kilograms will go down and that will now pull this 12, or how do you know if that is the other way? This 12 will go down and it will pull that 5 kilograms up. Okay, so by the way, we are considering here a pulley which is also frictionless, because sometimes there will be a friction which is experienced because of this pulley. But let's say that pulley is very smooth. There will be no resistance because of that pulley. Okay, that is flowless. The rotation of that is flowless. So we will not consider the friction there also. Okay, so we will try to cut. If I will cut this string here, let's say I will cut it there. Okay, by the way, first let's try to assume a direction of motion, and that is my assumption. Okay, let's say that the 12 kilograms will slide going down, and that will pull your ball, it will go up. So that is the motion that I will assume, and then let's try to see if that is correct based on the signs of our answer. So if you will try to cut these 5 kilograms there, let's say I will try to cut the string. By the way, the force that is experienced by the string here is the same as the force experienced by that string, because this is a single string, isn't it? This is a single string. So that is your important points to remember in your number 2 here. Okay, that is what is being, number 3. If we are considering a single string, all the parts of this string is experiencing the same amount of tension or force. Okay, so the tension that is experienced here will be the same as the tension that is experienced there. So you can cut anywhere, but first, of course, we will cut it here. So we will expose there a force which is the tension. What else? What other force in our system? Okay, this is our system for the meantime. Okay, what other force that is available there is, of course, do not forget always the weight of the object itself. So it says there is a 5 kilograms mass, but that is not the weight. Do not again confuse yourself with mass and weight. That 5 kilograms is a mass. Okay, by the way, how do you know that what is given is mass? Mass is kilograms, grams, or what do we call this one? In English, that could be by the way, do not be confused. In English, you have a pound force and a pound mass. The pound mass is the one which is equivalent to 2.2, equivalent to 1 kilogram. That is the mass. We have the force, which is actually different thing. So again, you can review that one, that is in your physics. So again, do not confuse yourself that 5 kilograms is a mass, since that is a unit of a mass. Then we need to convert that one into a force, which is the weight. It should be in newtons or kilonewtons. It depends on the value that we need. So again, you have the tension that is applied on the system that is pulling that to 5 kilograms upward, and of course its weight, which is directed always downward. A weight is always downward in the direction of gravity. So here, if you'll try to focus on the solution, we need to solve parameters, every unknown parameters here. Isn't it? This is the assumed direction of motion. That 5 kilograms will go up because that 12 will slide down. So your direction of motion in this part of the system is going up. So going up is positive, going down is negative. So at 5 kilograms ball, summation of forces y, or summation of forces vertical, that is of course equilibrium equation if you're statics, isn't it? So that we will solve the forces, we will satisfy the equilibrium. So let's summate forces y, or vertical, and isn't it that it says there that that is your second law of motion, the net force. We will go back there. We will not just equate that one to 0, since actually we cannot solve anything. Is that the acceleration or the net force? What's that? Ito, in this formula itself. Okay, the force is equivalent, or the force that is experienced by the system is equivalent to its mass times its acceleration, since we are now on moving object. That is not just a static, wherein if you will apply a force, all you need to do is satisfy the equilibrium. But here there is already a movement, so there is the incorporation of your kinematics, wherein that is acceleration, velocity, or distance. But of course, in our Newton's law, what we can find only is acceleration. Okay, so we will go there. Where's that? Yeah, okay. So summation of forces, the equilibrium, the net force or the resultant force, because of course you have their different directions, you need to find the resultant, the prevailing forces. Okay, so summation of that is T going up, so that is positive, and that weight is going down, so that is opposite the direction of motion, so that is negative. So whatever the result of this, that is the force on the system of 5 kilogram ball. That is the net force applied on the 5 kilogram ball for that to move. So again, the force applied on the movement is equivalent to the mass of the object on the movement times the acceleration of the movement. That is your second law of Newton, isn't it? So again, you cannot just say use T is equal to ma, because T is not just the force on the system. You need to find the resultant, and that is by summating vertical, since our movement is vertical. So if I will summate that again, T is positive minus the weight. Let's say that is weight 1, because there is another weight later on, so let's put their weight sub 1. So first, you need to know what is T. Actually, that is the unknown, so we do not know that one in the first place. But can we solve the weight? Actually, yes, because we are given the mass. So again, let's first solve that weight 1, weight of the 5 kilograms, so multiply that 1. Since again, we are on kilograms, okay, we are on kilograms, so we will be using the gravity, which is 9.81 meter per second, not the 32.2, because that is in English. So kilograms times meter all over second square, recall your physics, that is your Newton, isn't it? Kilogram meter per second square is your Newton. Okay, and we have here the commonly used, which is kilonewton. What is kilonewton? That is 1000 Newton, just like kilograms and grams. So 1000 Newton is 1 kilonewton. But your Newton is equivalent to kilogram meter per second. So if I will multiply the mass, which is 5, to your 9.81, that will be 49.05. And that is your force or your weight, which is in newtons. Okay? So if I will substitute that in our equation here, your mass, okay, your m, isn't it, is 5 kilograms. So I will change that one. But your acceleration is unknown. So in our resulting equation, you have there T minus 49.05 equals 5 times A. So there are two unknowns. So we cannot solve here T or A right away. We need to have another equation. That's why we need to make use of the other parts of our system, which is the free body diagram of your 12 kilograms. Okay, so if we will try to draw this one, this will be a little bit complicated, because that is now lying on an inclined surface, and that is attached on a surface, so there might be a friction. However, in this problem there is no friction, because maybe that is smooth. Okay, so if you try to draw this one, that is inclined, so this is important, guys. You will not always follow the x and y axis, which is vertical, horizontal. It depends on the inclination. So since that is inclined at a 30 degrees, then we will consider this as our horizontal, or I will tilt also my axis. This will be my x-axis and that will be my y-axis. Or you can say that is my horizontal and that is my vertical. Since what we are referring here, guys, is the contact point of the object. So the force here, the friction in the force normal is actually reckoned on the surface. So if that is inclined, then the normal force, as I've said a while ago, is always perpendicular to the surface. And where do we use that normal force? The normal force is the reaction which causes the friction. So it is always important for us to follow the inclination of the surface. Okay, so if I will try to tilt that one, I will tilt my axis so that this surface which is inclined 30 degrees from horizontal will now be my x-axis, therefore the perpendicular to that is my y-axis. However, okay, the weight of that 12 kilograms, if I will convert that one into a weight will always be directed towards gravity, which is always vertical, straight vertical. It will not be inclined even if that is inclined. Weight will always be downward. Okay, so therefore, if that will now be my weight, then isn't it? It is not parallel to x. It is not parallel to y. So if you will try to recall your statics of rigid bodies, you cannot summate here x and summate y because in the first place your forces is not parallel to x or y. So you need to break this down into components, isn't it? Break this down into its component x and y, or vertical and horizontal component. So that's why I break this down into two. A force that is actually parallel to your x and a force that is parallel to your y. Okay, resultant, guys. If you want to combine this back, then all you need to apply again is Pythagorean theorem for you to get your resultant. That is physics, and that is actually, yes, that is discussed in your physics, and that is also discussed in your statics. But we need to break this down into parallel to x and parallel to y so that we can use that in summation. So if you'll try to look at our system here, the weight or the force, the what do you call this one? The component of the weight which is perpendicular to the surface, that will cause the normal force. Okay, that is the force applied on the surface. So you will expect the reaction that is applied on the opposite direction. So that is our normal force. But if there is no such force perpendicular to the surface, then there is no normal force, then there is no friction force, because friction force depends on the normal. Okay? So however, there is a component directed perpendicular to the surface, so there will be a normal, and then there will be also a friction. However, it says in the problem that is frictionless because maybe there is no roughness in your inclined surface. So we can actually forget about the friction force for now, for this example. But what we need here, okay, so look at this. If I will now try to get the component of that parallel to x, then that will actually deal with your T, your tension, isn't it? If I will cut this one, if that is T, the force experienced by the 5 kilograms, that is also T, the same T experienced by the 12 kilograms. Okay? So if that is T, then that should also be T. That should be the same since that is a single stream. Okay, so we do not have any problem here regarding your Y since there is no friction. So there is no coefficient of friction, so that means that is frictionless. So we can now forget first about friction. So maybe there is no use of summating Y there since we do not need there anything. But there is a use if we will summate your horizontal. That is where we will be having your second equation. So summate forces parallel to x, then of course you will end up there with resultant, and that resultant is the force applied on the system so that there will be a movement. And because there is a movement, the resultant force is equivalent to the mass of the object times its acceleration, always, since there is a movement. Okay, so summate tayo. So that is the direction of motion. It is going clockwise, so the direction here is that will slide down. So that is a positive distance. The one that is slide down, that is the positive. So if that is the positive direction, then T is the opposite, so that is negative. So what other force? Of course, again, you will see there a friction which is also opposite, which is negative, but again, there is no coefficient, so that is useless. But what else? What else is parallel to x is the component of your weight. This is component of your weight. Isn't it? You will break this down. Actually, if that is 30 degrees, this force here is the same as the force for us to close the right triangle. Isn't it? So if I will break this down, this weight 2 into this parallel to y, that is actually its cosine. But what we need is this opposite to the angle, so that will be sine. So the component parallel to x, which is this one, the same as that, is equivalent to weight 2 sine 30 degrees. That is just Pythagorean theorem, guys. I mean not Pythagorean, that is just right triangle. Okay, so that equivalent of horizontal force or parallel to x is weight 2 sine 30. So that is this one, positive. Why? The same direction that is going down the plane to your assumed direction. So positive tayo dyan. But first, we need to solve your weight 2 since that 12 is just a mass. So multiply that one by 9.81 kilogram meter per second square. That will now be again a Newton. So if you will multiply this one, that is equivalent to 117.72 newtons. So substitute whatever we have in your equation so that you will have your equation 2. Okay, so again, this is just the explanation. If there is a friction, that is just equal to fun. Friction is fun. But since there is no, that is frictionless, so friction is 0, so that is useless. But again, substitute your weight 2, which is 117.72. You will have here negative t. F is cancelled because that is 0. Plus weight 2, which is 117.72 sine 30 equals, isn't it, that is equivalent to mass acceleration. We know your mass to be 12 and your acceleration, which is another unknown. So you have another equation which is in terms of t and acceleration. So that is now algebra, guys. I will not be showing you that one. You have equation 1, which is t and a. You have another equation for that, which is t and a. So two equations, two unknowns, algebra, solve simultaneously. You will end up here with a tension, which is positive 51.935 newtons. And then an acceleration, which is 0.577, and of course, since the unit of our motion or acceleration of gravity is meter per second square, then that will be in meter per second square. So again, in the first place, there is no problem with our unit because everything is in kilograms, meter, and seconds. But let's say that is not kilograms, that is grams. We need to convert that one into kilograms because Newton is kilogram meter per second square. Okay? So, or let's say you have a distance there. Let's say there is an included distance to be in feet, but you are having in meter per second. So you need to convert that in meter. So again, just like in kinematics, try to make your units align with each other. So again, I will not show you how t and a solves, and that is algebra. That is just two equations, two unknowns. So you can check that one. And what we will be getting, value of t and a is positive. So what does that mean? The assumed direction is correct. So it will really slide down. This 12 kilogram will slide down and it will now pull that 5 kilogram up. But again, if your A is negative, it means the direction of motion is just the other way. Your T will never be negative, guys. Your T will never be negative because your T is tension. That means it is stretching the cord, which is the true scenario. That could never be negative because what is negative force? That is compression. It cannot be that your cord is being compressed because, isn't it? It is being stretched by the 5 kilograms and 12 kilograms. So that tension will always be positive. Unless, again, that will be a different, but that will not happen. It will never be compression because look at the system. That will slide down, this will pull down. Okay, so design, you can decide that one if that is different direction by looking at the acceleration, and that is positive, so we are correct. So these are your values, the unknown, magnitude index of acceleration, and the tension of the cord. Okay, let's have one more example for this. So three bodies A, B, and C. So again, this is your figure, the same, almost the same actually. This is the common application of your second law of Newton. Okay, boxes, friction, strings, and so on and so forth. So three bodies A, B, and C are connected by two cords. Okay, so as you can see, this is the first cord connecting A and B, and then this is the third cord that is passing at the pulley connecting your B and C. And then it says there, so that the three bodies will move with the same acceleration. Yes, so if A moves at that acceleration, that will be the same acceleration all through with your B and C, because again they are connected, so they will act as one system. So the movement of the other will be the same movement of the other 2. So the pulley is assumed to be weightless and frictionless. Okay, let's assume that the weights of the pulley and the strings are negligible, okay, compared to the weight of the object itself. Because of course, if you are using a heavy, if you are using a heavy cord or a string, there will be an effect. But since let's say that is negligible, since let's say that is very very thin, then we can neglect it. Okay, body A weighs 36 pounds. So we are now in English unit. Again, you need to know what is pound force, pound mass. They are very, very different things. Okay, pound force is a force, pound mass is a mass. So weighs, it says there weighs, so that means that is a weight. Okay, if it says there that the mass of A is 36 pounds, then that is a pound mass. But it says there weighs. So you need to know what is the mass and weight. So this is a force already. Okay, the given for A is a force already, and of course that will be the same to the rest. So B there is 60 pounds and C is 120 pounds. Okay, so you have already the weights of these 3 boxes. And then the friction, the coefficient of kinetic friction. Okay, so you have now a coefficient of friction, so you will experience now a resistance, which is your friction. So the kinetic friction for A, so there will be a friction, of course, with your A, because that is lying on the surface. So there will be a resistance because of that, and that is equivalent to 0.25. So that means that is 25% of whatever normal force acting on the surface. And for B, the plane that has a kinetic friction coefficient of 0.2. So maybe why is it they are different, but they are passing on the same surface, isn't it? Maybe because the surface of your box A is rough, or more rough compared to the surface of your block B. Maybe this is smoother, this surface of your block B. So even if they are passing on the same surface, but of course their surfaces individually are different, so that will affect the friction. So for A, that is more resistance because that is 25%. For B, that is just 0.2, or that is 20%. Of course, there is no friction in your C because that is hanging, that is not attached on the surface. So what we are going to find here is the acceleration of the bodies. Of course, only single acceleration since they act as one. So the acceleration of A is the same as B is the same as C. And then the tension in the cord between A and B. Okay, so find the tension experienced by this string connecting A and B, and then another tension connecting B and C. Are they different? Question there, are they different? Actually, by merely looking at the figure, you can say that they are different. Why? Okay, let's try to analyze. If you will try to consider this string connected at A and B, whose weight is being carried by this string? It is just the weight of your block A, if ever that will move this way, isn't it? Because if that will move down, then actually that depends which one is heavier. So maybe this will be useless. So so that will now give me an idea that maybe the direction of motion is this one, clockwise. But you can actually consider different. But for me, I will consider this one. So again, the weight that is being handled by this string is only the weight of your A, since that is, let's say, that is being pulled. So this will only exert effort for your box A. But your second string here is actually carrying the weight of your block B, and so with your block A. So you will expect a different tension here and the tension there. But of course, this tension here is the same as here because that is just a single string. Okay? So again, that is our unknown, the acceleration of the bodies, and then tension connecting A and B, and then tension connecting B and C. Okay? So again, as I've said before, cut this down into parts and then expose the tension and then analyze the system. So, but first, since later on we will be needing the mass, what we are given is a force, isn't it? The weight. Unlike a while ago, what is given is kilograms. That is by merely looking at kilogram, that is already a mass. So we needed the weight also, because in your formula, isn't it, force is equal to mass acceleration. So you need your weight, you need your mass. So you need to always have that both. So since we are given weight, we need first to solve each mass of this one. So 36. Solving your mass is of course divide, since if you are solving your weight, multiply. So divide by gravity, that is pound. So we will be using your 32.2, which is English equivalent of your gravity, 32.2 feet per second squared. So you will end up here with 1.118 slugs. By the way, okay, please be careful with this. Do not say that the mass of a pound force is a pound mass. No, that is different. Where's my pen? A pound force, isn't it, okay? Newton is kilogram meter per second squared. Pound is the equivalent English unit of force. Okay, that is slugs. There is no abbreviation for that. Maybe there is, but that will be on the other book. So let's follow the complete slugs times feet per second square. That is the equivalent of your pound force. This is very, very different from your pound mass. What is pound mass? This pound mass is actually 1 kilograms is equal to 2.2 pound mass. That is your pound mass. Your pound force is different, because actually, if you try to look at this, if 1 kilogram is equivalent to 2.2 pound mass, then 1 kilogram is heavier than 1 pound mass. But if you try to compare kilogram with slugs is far heavier than kilograms. So please do not be mistaken this pound mass to be the slugs. No, slugs is different from pound mass. So please take note of that, so that we will not be confused with our units. So let's say if you are given a pound mass, you need to convert that one into slugs so that you can make use of pound force. There is a certain conversion of pound mass with slugs. Or if I were you, I'd rather convert a pound mass into kilograms, since that is as simple as 2.2. So 2.2 pound mass is equivalent to 1 kilogram. So if you will convert the pound mass into kilogram, then what you will be using as gravity is 9.81. So again, that is just manipulating your units. So that is physics. Okay, so solving your masses. So mass A, 36 divided by 32.2 is 1.118 slugs. And your B, 60 divided by 32.2 is 1.863 slugs. And then weight of C, or mass of C, is 120 divided by 32.2 is 3.727 slugs. So those are the masses. We need that one in your F is equal to MA. So let's try to break down the system. So let's focus on your first block. I will cut the string here. You will expose the tension. So let's put there T sub 1, and the tension here is T sub 2, since they are different. Do not just use T, because of course they have different values. So let's say T sub 1 and T sub 2. Okay, so this is my free body diagram here, and my assumption is that will go this way, so that is the positive direction. So in our free body diagram at A, the positive direction is going up. Okay, so again, inclined, so this is my X, let's say that is my X-axis, that is my Y. Okay, so break down the weight, since weight is directed downward, so break that down into equivalent components. X component and Y component, and the angle here is 30 degrees, so the angle there is 30 degrees. Okay, by the way, how is that done? Because actually you'll try to go back here, that is the same 30 degrees, this is 30 degrees. Okay, I will show you how that is done, because maybe you will be confused with this. So how is that is the 30 degrees? For example, this is our 30 degrees. This is 30 degrees. and you are considering a perpendicular axis to that, so that you will have your x and y. This will be x and y. And of course, that will be, this is horizontal, this is it. Let's say the weight is applying directly downwards. So you look at this. If this is 30, what the remaining here is 70 degrees, because this is 90, isn't it? Isn't it? These are intersecting lines. So opposite angles are the same. So if that is 70, then that is 70. And of course that is 90, since that is perpendicular. So if that is 70, what's remaining here? That is 30 degrees. Okay? So let's say this is the weight. You are trying to break this down into parallel to y, which is this, and then perpendicular to y, or parallel to x, which is that. So you can actually make use of this also as the 30 degrees if you want. So there are a lot of ways to break this down, but that is just trigonometry. So that's how we ended up here with 30 degrees. So the same here in your second example. If this is 30, then that is 30 degrees, or if you will use this angle, then that is 30 degrees also. Okay, so break this down. X component, y component, we will be using that y component to solve your normal. Okay, let's put there sub a, since we have another normal later on. And for the friction, we will consider this sub a also, so that we will, because we will be having another later on. Okay, so this is a free body diagram for your block A, wherein in block A we have a coefficient. So there is a frictional force or resistance, which is 25% of the normal. So summate. Positive is going up. So what other forces? Of course, tension, that is positive. What else? The component of the weight, which is downwards, because look at this. This is going down, so that is the components. That cannot be going up, because if that is going up, the direction should be this one. So that is against your motion. So minus, what is again the component that is actually the same as this, so that is sine of 30. So weight of 8 sine 30. And then minus, what else? This friction. We have already a coefficient, so we have a friction. And the friction is always opposite the motion. So if that is going up, your friction is against. So that is also negative. So again, what do we need? Weight. We already solved. That is already given, isn't it? Weight of A is 36 pounds. How about your frictional force? That is, okay, force is equal to Fan, isn't it? We are given the kinetic, since of course we are already on moving. Okay, so mu A, that is our, what do we call this one? 25, or 0.25 or 25%. So what is the normal? We need to know the normal. So in the first place, we need to know N. Before we can solve your friction, we need to know your normal first. So how is that? Where do we get that normal? That is actually because of the y component of the weight. That's why we have a normal. But if there is no component just like that, we do not have a normal. Therefore, we do not have a friction. Okay. However, there is a perpendicular to the surface, so there is a normal. So summate, this is the only force. So let's say that is the negative. So and that is positive. Equate that one to 0. You will end up with the normal force or the reaction of the surface to be weight of A cosine 30, because this is the component is cosine 30. So your NA is 36 cosine 30 degrees. 36, that is the weight, isn't it? So if that is your normal force, then F is equal to FUN or UN, mu N. Your mu is 25.25. So your F is 0.25 times 36 cosine 30. So you'll end up there with, actually you can solve this one as 7.794. And since we are using here a 36, your weight is in pounds, so you will expect the force which is in pound, friction which is in pound. So now substitute everything in that equation that we have here on top. Tension 1, we do not know that one, so that remains unknown. Weight is 36 sine 30. And then of course your friction, we solve that one to be 7.794. And then your MA, isn't it? MA, M, your mass of that, we computed that one a while ago to be 1.118 times the acceleration, which is unknown also. So simplifying this further, so simplify lang natin siya. Let's try to put every unknown on this side. So T1 and then of course 118A. It will go positive here. I mean negative here. This will combine. If you will combine this one, that will equivalent to negative 25.794. Okay, let's check that one. That we will not be having wrong answer. 36 sine 30. No, sine 30. 7.794. So that is negative 25.794. It will go positive 25.794 on the other side. So this is the equation 1, which is actually in terms of T1 and A. So now we did not yet solve any of this. Let's proceed with the next block. Let's try to go at B. Okay. I will draw the free body diagram there. Isn't it that there is a T because of the string connecting A and B, that is T sub 1. Of course, there will be a T also that is the same, since that is the same chord connecting A and B. So if that is T sub 1, then this is T sub 2. That is a tension. So if you say tension, that is always away from the object. That is tension. If that is compression, that is towards the object. But again, as I've said, string is always a purpose of tension. It is not for a purpose of compression, because a string cannot actually resist a load in compression, because that will just of course buckle. Okay. So T sub 1, there's a T sub 1. That is the transformation of our T sub 1 here. So what else? Of course, if I will cut the string there, you will have another T, but do not say that is T sub 1, since I have explained that is different. So let's say that is T sub 2. What else? Your weight. We need to break this down onto y and x components. So here we are. Now let's try to have again your mu there is 20% or 0.2. So again, summation of the forces on x is equivalent to, by the way, why are we summating forces on x and that is equivalent to ma? Why not summation of force of y? Because the motion is along the x-axis, not along y-axis. So we will be summating the resultant force in your x, because that is the motion, not along the y. Okay? So you do not be asking me, sir, why is it not summation of fy? Okay? So again, these are the forces on the system. So you have there again always a normal and a friction. Since there is a force directed on the surface, there will be always a normal. And since there is a coefficient, then there will always be friction. Okay, so friction is always against the motion. That is still going up. Motion is assumed going up. So what else? So summate. Let's try summate. T sub 1 is again so negative. T sub 2 is going to the motion, so positive. What else? The x component of weight is going down, so against, negative. And then the friction is against also, which is negative. And of course, mass A. Our mass there is, we computed that one, 1.836. So that is 1.836 A. A is still unknown. So we need to know your friction, which is equal to Fan, and U is 0.2, and then N, we need to compute that one by summating Y. So what are the forces in your Y? That is just the Y component of weight, and then of course the normal force. So playing around, normal force is 60 cosine 30. Your weight for B is 60, isn't it? Yes. So 60 cosine 30. So therefore, multiply your mu to that value, you will end up here with 10.392 pound. That is our friction in this B, block B. Okay, so substitute now. T1, T2 is still unknown, of course. Weight is 60. And then our friction, that is 10.392. And then 1.836 times A. Okay, rearrange every unknown on this side, left side. So negative T1, positive T2, and then that will go negative 1.836A. Combine this one. Okay, let's try to check again. 60 cosine 30, 10.392. That should be 62. Oh, no, wait. 60 sine, not cosine. Sine 4392. Okay, so that is negative. Actually, combining this one is negative 40.392, but it will go positive. This will go negative also. So there are three unknowns. A while ago, our unknown is T1 and A. Now we have another unknown, which is T sub 2. So we cannot just use two equations, two unknowns, since actually the unknown on the system of equation are three, T1, T2, and A. So you need to have another equation. So we need to go to the third object. So now in our C, this is simple. In C is simple because there is no friction, there is no surface attached to that. So that is just actually copying this one. If that is T2, this is also T2. Okay, let's go there. So cut that one, you will expose the area T sub 2. So this is where we will create your third equation. Okay, so there is no x and y here since that is just vertical. So summate forces here, which is equivalent actually to the motion is going down since that is clockwise, isn't it? So positive is going down. So summate that one, T sub 2 is negative, it's against. The weight, see, you will not convert this one into a component since again it is not inclined. Okay, our motion is assumed to be vertical, so that is parallel, so no problem. So that is positive since that is going down, and that is mass times acceleration. So your mass here in C, we computed that one to be 3.727. Let's check. 3.727, yes. So that is our equation. Oops, equation 3. Okay, 3.727A. So playing around with this one, your weight C, that is already given to be 120, so that will go negative. Okay, all the unknown on this side, this will go negative. So you have your third equation. Okay, you have three unknowns, isn't it? T sub 1, T sub 2, and A. So you need to have three equations. So algebra again, by substitution, by elimination, whatever process you will be using, solve simultaneously, you will end up with T1, T2, and A to be these values. T sub 1 is 34.8 pound and T sub 2 is 89.98. So what can you say? It is true. Why? As I've explained a while ago, going to the total system, the tension here is less than supposedly because that is just holding the weight of A. And the tension here should be greater because that is holding your A and B, which is true in our value. It is positive since that is tension. Okay, so no problem. How about our acceleration? Acceleration is positive, therefore our direction is correct. So that is our answer. So if you have any question here, okay, you have an activity of course to be doing. You will try to look at that activity in your module. Okay, so this is the important concept here. Okay, so again, the assumed direction of motion. If there is no direction, there is no obvious direction. Always assume, and that assumption is always the positive value. If your answer is negative, that only means your assumption is wrong, but your value is still the same. Okay, what else? Drawing the free body diagram of the system is always recommended to help in the analysis of the problem, which is actually very, very true. Because how will you know the equation if you cannot bring out all the forces on the system? And you can only bring that one by drawing your free body diagram and of course by breaking down your system into parts. Especially your tension, you cannot show that one without cutting the string. So that's it. If you have any question, again, comment below or prepare for our next live meeting for that to be answered. Thank you very much for watching.